Welcome back, students. In this section, we are going to look at the quantum mechanical rigid rotor. So just like our harmonic oscillator served as a convenient model to talk about vibration, the rigid rotor will serve as a convenient model to talk about rotations. So the learning goals for today are going to be just like last time. We're going to solve the Schrodinger equation for the rigid rotor instead of the harmonic oscillator. In some ways, this solution is going to be simpler, and in some ways, it's going to be much more complex, mainly because we have to deal with multiple dimensions, unlike last time. We can make comparisons, as always, to the particle in the box, and we're going to see the quantum numbers L and M sub L come out here. We use different quantum numbers and for other things like vibration to distinguish between the two. And we'll want to be comfortable working with the wave functions we get at the end of the day. So we won't actually get to these wave functions today. We'll save that for next time. But we're going to go through all the process of solving for them, especially for three-dimensional rotation. All right, so having discussed last time vibration with translation before that, we're now going to focus on the last degree of freedom that molecules have, that is rotation. Just like for vibration, a molecule that is able to rotate needs to have at least two atoms. Single atoms can't change when they rotate, so they don't have rotational degrees of freedom. We'll start with a classical picture, just like last time, and adapt the model to quantum mechanics. Mathematically describing rotation is more complex than for vibration because we have to deal with multiple dimensions, and that has a whole nother dimension, you can say, that we have to work with. To keep things simple for ourselves, we'll start by considering two-dimensional rotation and then move into three-dimensional rotation, which is more applicable for molecules. Just like for the harmonic oscillator, our rigid rotor is only going to be an approximation. So the rigid rotor implies that our bond is rigid as it rotates and isn't changing. The whole point of our last lecture was that bonds vibrate. So we know very well that the bond is not actually rigid. And it turns out that the real deviations between things like the rigid rotor and the harmonic oscillator and how real molecules have coupled vibrations and rotations provide slight differences to the ideal in terms of their spectra. So we can extract these constants for how these things are coupled and then use that to actually identify molecules. And so we'll look into that as we start talking about spectroscopy, and we'll do some of this in our labs. So the things that we use in our rigid rotor model are going to be R, which is the bond length. And here you can see we haven't yet made change of our center of mass coordinates. And we, of course, will use the center of mass coordinates. So just like before, we'll use mu, which is the product of these two masses divided by the sum of these two masses. And that gives us R is the bond length, or the sum of these two little R's here. So for rotation, again, this may not be obvious, but rotation is simply motion that's confined to a circle. And as the fact that it's just motion, rotation is pure kinetic energy, just like translation. So we can draw some conclusions from how we described the free particle is that, one, there is no potential energy. So there is no force that opposes the free rotation of these molecules. However, unlike translation, we will still have boundary conditions in that we have some sort of circular motion that means something. So to solve the rigid rotor problem, just like for the harmonic oscillator, we're going to use center of mass coordinates. And then it turns out, and you may be familiar with this from physics, that it's much simpler to use polar coordinates or spherical coordinates for 3 dimensions to talk about rotation rather than trying to use single dimensions. So our distances become angles, and here we can see an angle described where we multiply the radius by the distance, and we can talk about how far this moves with respect to x in terms of how far it moves based on some angle. And then we can similarly convert things like velocity and acceleration to angular velocity or angular acceleration. The one that's going to be most useful for us, it turns out, is surprisingly linear momentum into angular momentum. So our linear momentum, which has the symbol P, becomes the angular momentum L. And I've written L, R, and P here in terms in bold to denote that these are in fact vector quantities. So the angular momentum L is defined as the cross product between the radius and the linear momentum P. And it turns out that for something like two-dimensional rotation, these two are both in the plane of rotation. So the radius is, of course, in the plane of the rotation, and then the motion is also in terms of the rotation. So if we look at this here, we see we have our radius, we have our velocity that is the same direction that momentum will be in. And so the cross product of these two is going to be perpendicular to both of them and will be sticking straight out of the page. So for two-dimensional rotation, the angular momentum is simply perpendicular to the rotation and it sticks out in the opposite direction. So if we took this rotation to be in the XY plane, our angular momentum would only be in the Z plane, the Z dimension. And with these new definitions of angular velocity and angular momentum, we can construct what the energy is based on things that are easier to calculate for rotation. So we know that the kinetic energy is equal to 1/2 mv squared. Here we're using mu because we're talking about the reduced mass. But we can convert this in terms of velocity to angular velocity. So if we plug in our definition here for angular velocity, we get 1/2 mu r squared times the angular velocity squared. And then we'll pool mu r squared into this new term I, where I is the moment of inertia. And this gives us a formula that looks very similar to our linear dimension. So linear momentum is linear energy is 1/2 mv squared. And here we have 1/2 I times the angular velocity squared. So you can see the connections between these two. Similarly, we can do the same thing with momentum. And so energy is equal to the square of the momentum over 2 times the mass. Here in rotation, we can substitute in what linear momentum is in terms of our angular momentum. And again, just doing that here, we get that the angular momentum is the linear momentum divided by r. So this will give us L squared over 2 mu r squared, or again, L squared over 2 I. So in rotation, our moment of inertia I, which is the mass times r squared, becomes the new kind of mass to think about this if we were using linear coordinates. And then we can use our angular velocities or our angular momentums to calculate things like the energy. So classically, there is no restrictions on the value of our angular momentum. It is a continuous variable, as we would expect from a classical system. As we apply this to quantum mechanics, we will of course see that this changes. At this point, you may find the concept of our angular momentum here hard to grasp, but we're going through it not just because I want you to remember, vector physics and rotation physics, but because our angular momentum plays a very important role in quantum mechanics. So our symbol L here, hopefully will get you to think about quantum number L. So as we apply this to quantum mechanics, we'll see that we have a quantization in L. And this is important for rotation, and it turns out it's also important for something like the orbitals of the hydrogen atom, where we have this quantum number L that determines something like if it was an S, P, or D orbital. And this is directly related here to the angular momentum. So that quantum number L determines the quantization in orbital angular momentum. So keep that in the back of your mind as we talk about this. I'm not forcing you to do L because I like it or I like angular momentum or anything like that, but because it actually is pretty important to quantum mechanics. And we'll see the connection between this L and then something like the orbitals in due time. So now that we kind of have a setup for rotation, the next step is going to be to solve the Schrodinger equation and see how this changes for in terms of quantum mechanics. So, well, again, we'll start with two-dimensional rotation because that's simpler, and then we'll move on to 3 dimensions. So we can construct the Schrodinger equation, and again, the potential is 0 because we have free rotation. So we simply have this kinetic energy term here. Now this looks pretty nasty because we have 2 partial derivatives with respect to x and y, which we have to do because we're talking about rotation. So like I mentioned on the last slide, it is simpler to solve these problems if instead of thinking about the Cartesian coordinates x, y, and z, we think about the polar or spherical coordinates. And so if we do a change of variables from Cartesian coordinates to spherical coordinates, or in this case, polar coordinates, we get a much simpler differential equation to solve. So I am not expecting you to be able to work with these sorts of things. I don't expect you to be able to change the variables from Cartesian to polar or spherical coordinates. But that is all that we have done here. So rather considering derivatives with respect to x and y, if we change to polar coordinates, we only have the angle that is changing. And in this case, the symbol that we use for angle is phi. So now our wave function becomes a function with respect to just phi, and our phi changes, our angle changes throughout rotation. And here we have an equation that we have seen before. And hopefully at this point, this equation is familiar to you and you are very comfortable with solving this differential equation. So in this case, what we need to do is take two derivatives of our function with respect to phi and return that function multiplied by a constant. And so we are very familiar at this point with the solutions. Just like for translation, it's possible to have two solutions, one that's corresponding to clockwise rotation and the other counterclockwise rotation. So we'll have two solutions that we'll call phi plus and phi minus. And they are, of course, as follows. So phi plus is going to be equal to some constant a plus times e to the I. And here we're going to use a different term. So we're going to pool all of these things together, and we are going to call that m sub L. And I'm putting that in these bars to determine that this is the absolute value of m sub L. And we'll talk more about that in the future. And then, of course, we have phi. And then we have our negative direction, our counterclockwise rotation, that is going to be the same here. So these are the potential solutions here. And then our m sub L is equal to all of these various conditions, just like we had k before. That was equal to all of these constants. So in this case, our m sub L is equal to 2 mu r naught squared e over h bar squared. And it's the square root of these things. And that's why we have the absolute value there. All right. So despite having no potential energy, which remember that usually gave us boundary conditions to ensure quantization, these rotating molecules are still bound by the conditions of rotation. And so what do I mean by that? Well, I mean that after a molecule rotates all the way around the circle, it is back in the same position that it was before, and its wave function must be identical. So another way to say this is that our wave function at some angle phi must equal the wave function at that angle phi plus 2 pi, one rotation around the circle. And so applying this condition will give us quantization conditions. All right, so what do? Well, we can say that, again, just plugging in these values and setting them equal to each other. So we'll do the a plus here. And if we plug in phi, at phi, we'll get a plus e to the I ml phi. That's great. And then if we plug in phi plus 2 pi, we'll get is equal to a plus e to the I ml phi plus 2 pi. In this case, what we're going to do is we're going to break apart that exponent. So we can say this is equal to a plus e to the I, I'm going to put that in parentheses here, I m L phi, and then times e to the I m L 2 pi. And that's, of course, just what happens when you add exponents. It's like multiplying them outside of the exponent. So here, in this case, we have this, which is the same as this, and our equation then becomes 1 is equal to e to the I ml times 2 pi. So when is e to the iml 2 pi equal to 1? Well, remember that we can use Euler's formula to change this imaginary exponential into sine and cosine functions. So this is equal to cosine of the absolute value of ml times 2 pi plus I sine the absolute value of ml times 2 pi. And when is this equal to 1? Well, the cosine argument is equal to 1 at integer numbers of 2 pi. And the sine is equal to 0 integer numbers of 2 pi. So if m sub l is equal to integer numbers of 2 pi, so 0, 1, 2, and so forth, then this will end up equaling 1, and this will equal 0. So our quantization conditions here are that the absolute value of m sub l is equal to 0, 1, 2, 3, and so on. Or in other words, that m sub l is equal to 0, positive or negative 1, positive or negative 2, and so on, continuing in that way. So in this case, we have a different boundary condition than our previous conditions, which gives rise to very different types of quantization. For example, we have negative numbers being possible. And again, that just is arising from the differences in our boundary conditions. To solve for the energy, we can just rearrange this expression here for what m sub l is, or again, take our expression and plug it into the original Schrodinger equation. Either case will give us that the energy, as depending on the quantum number m sub l, is equal to h squared m sub l squared over 2 mu r naught squared, or we can write that as h squared m sub l squared over 2 times the moment of inertia I. Here we see that the energy levels are based on the quantum number m sub l. Now you might be wondering, why are we using m sub l instead of just something like m? And it's because this m sub l is going to be related to our quantum number l in some way, and we'll see that as we go forward. So hold on to that question for now. Since the energy is dependent on the square of m sub l, the energy levels are twofold degenerate in as long as m sub l is non-zero, meaning m sub l of -1 will have the same energy as m sub l of 1, despite having different equations. So in this case, we can only measure the energy. So if we measured an energy that was h squared over 2I, that's consistent with a quantum state with either m sub l of 1 or m sub l of -1. We can't distinguish between the two, and so we call those energy levels degenerate. So some things to observe is that we have no confinement here. And so our particles aren't confined to a box, and as they're not confined to a box, despite having this quantization condition coming from rotation, there is no 0 point energy. So there is a 0 energy allowed at the quantum number 0. Let's look at some of these solutions, what these equations would look like. Here we can see, again, we're basically imposing sine functions on top of rotation. So here what some of the different quantum numbers would do to the rotational wave functions. We're confining these waves to circles. Another interesting thing to point out is that for two-dimensional rotation specifically, the angular momentum is completely described by the z component. So when we're rotating in 2 dimensions, the angular momentum being the cross product of the linear momentum and the radius there of rotation is in a completely different dimension. In this case, we take that to be the z dimension. And the angular momentum operator for the z dimension is negative IH bar times 1 derivative with respect to phi. So if we were to operate on our wave function with respect to the z component of the angular momentum, what we see is that we would take 1 derivative of this, and we return our same function multiplied by a constant. So what does this mean? Well, it means that for two-dimensional rotation, we can know the angular momentum, the z component of the angular momentum, and the total energy all at the same time, because all 3 of these operators commute with each other. And they're all eigenfunctions. The wave function is an eigenfunction of all of these operators. Another thing that we can say is that, again, we've seen this before. Classically, we expected that the energy is equal to the square of the angular momentum over 2I. And we can see that here as well, as the angular momentum is mLh bar. So that squared is h squared ml squared. And then over 2I gives us the same as the energy. As we'll see, we'll look at three-dimensional rotation next, and we'll find that this is not true for three-dimensional rotation, because this relationship is only true for two-dimensional rotation. So it gets a little bit more complicated when we look at rotation in 3 dimensions, and we'll see what we can see for that case next. All right, so three-dimensional rotation, what can we do with this? This introduces a third dimension, which of course drastically complicates the dimensionality of this problem. So we'll introduce a second angle theta. So here for our two-dimensional rotation, we have phi, and phi goes around this circle, this sphere in the whole way around the circle. So that goes from 0 to 2 pi, and theta goes from 0 to pi, so all the way from positive z to negative z. And with those two restrictions, these two angles can fully describe all 3 dimensions of Cartesian coordinates, of course, with a radius r. So our Schrodinger equation for 3-dimensional rotation looks much more complicated than our equation for 2-dimensional rotation. And of course it is, and the solutions are correspondingly more complicated. So we get this expression here, and we'll go through some steps to solve this. Now, just like for the harmonic oscillator, we are not going to be able to solve this by ourselves. However, we can do some simplifications that gets us into a state where we can see what the solutions would likely be. So we'll go back to the board and we'll simplify this in some way. And what we'll see is that we can achieve a separation of variables, just like we could before. The first thing we're going to do to solve this equation is multiply all of these constants over and then pool them together. So we'll get this term beta that we'll say is equal to 2 mu r naught squared times the energy over h bar squared. And when we do this, we get the following. We get 1 over sine theta times a partial derivative with respect to theta of sine theta times a partial derivative of our solution. It's here we're using the y as our function. And so our function of theta and phi times another derivative with respect to theta, plus 1 over sine squared theta times 2 derivatives of y, in this case with respect to phi. And that's equal to beta times y, theta, and phi, or minus beta there. And what we'll do now is multiply every part of the equation by sine squared of theta. And so if we do that, right, if we multiply by sine squared of theta, we'll remove this. We'll get a 1 sine theta on this side, and we'll get a sine squared theta on this side. Then what we'll do is rearrange. So we'll bring this term over here and bring this term over here, and then we'll end up with our derivatives on one side of the equation. So what we'll get is the following. We'll get sine theta times a derivative with respect to theta of sine theta times another derivative of our function with respect to theta and phi of theta, plus beta sine squared theta times our function of theta and phi. And then this is going to equal negative the partial derivative, or 2 partial derivatives of our function with respect to phi. And we've arrived in a place that we've been at before. What we have is an equation, and on this side of the equation, we only have derivatives and functions with respect to theta. And on this side, we only have functions with respect to phi. So we're taking derivatives with respect to theta of our function and taking derivatives with respect to phi of our function, and they are equal to each other. So if that is the case, these derivatives must both be constant. And they also we also must be able to separate our variables. So what that means is that our function y of theta and phi, we have to be able to break that apart into a function that's only based on theta and a function that's only based on phi. And we can then rearrange and solve both of these equations separately. So when we do that, of course, on the theta side of the board, our phi functions are going to come out of the equation and they're not going to be involved in the derivative. So we would get phi as a function of phi times sine of theta times one derivative with respect to theta times sine of theta, and then times another derivative of our theta function with respect to theta. And then we'll have plus b or beta sine squared our function of theta times our function of phi. And then on the phi side of the equation, we'll simply have negative our function of theta times two derivatives of our function of phi with respect to phi. And then, like we did for our three-dimensional particle in the box, if we divide by the total here, if we divide each side by theta and phi, we'll remove all phi dependence from this side and all theta dependence from this side. So dividing both sides of the equation here by theta with respect to theta and phi with respect to phi, we end up with the following. We get 1 over our theta function times sine theta times a derivative with respect to theta of sine theta times the derivative of our function with respect to theta plus beta sine squared of theta is equal to 1 over our function with respect to phi times two derivatives of our function with respect to phi. And so again, in this case, we saw what we said before, is on this side we only have thetas, and this side we only have phis. And for these this equation to be true, both sides of this must equal a constant. And the constant that we're going to say this is equal to is m sub l squared. The phi side of this equation is the exact same equation as we had before. So if we rewrite this, we'll see that we have two derivatives of our phi function with respect to phi is equal to, sorry, I forgot this negative up here. So here it's equal to negative ml squared times our function with respect to phi. So the exact same solution we saw for two-dimensional rotation, and that's why we write it in this way. Now, the y component is much more challenging, and we'll go into what the y component looks like next time, but the y component is the spherical harmonic functions. So you can look ahead in your book if you want. We can talk about this in class, and we'll also see this in the next lecture, what these y components are. But we'll see that these y components depend on the quantum number m sub l. The boundary conditions that we're going to apply are the same one that we have seen before. So y must be a single valued function and needs to have a finite amplitude. But the way in which these are applied are pretty complicated. So we're not going to go over them. We're just going to state the quantization conditions that arise from this. And what we'll see is that beta, which remember beta is the energy is related to beta here, becomes or is dependent on the quantum number L in the following way. It's L plus 1, where L is equal to 0, 1, 2, and so on. And then our m sub L quantum number is also dependent on L. So m sub L is 0, plus or minus 1, plus or minus 2, all the way up to plus or minus L. And this gives some interesting relationships here between these two quantum numbers. And we'll see this next time. So we'll write out our spherical harmonic functions as y depending on two quantum numbers, L and m sub L, as a function of theta and phi. In this case, they're equal to a theta function, which is also dependent on both quantum numbers, L and m sub L. And then our phis that are only dependent on the quantum number m sub L. And we already kind of know that our phi functions as a function of m sub L are equal to e to the I ml phi. And that is, of course, the case. We don't yet know what these theta functions are, but we'll see them. So the need for two quantum numbers here comes back to the fact that we have a two-dimensional problem. We can change in two angles, so we have two quantum numbers. Just like for the three-dimensional particle in a box, we had 3 dimensions that our particle could move in, and we had 3 quantum numbers, nx, ny, and nz. However, in this case, for rotation, these quantum numbers L and m sub L are linked. Now, something that we can note here, again, we had what this beta constant is, but recall that our beta is equal to 2 times the moment of inertia times the energy over h bar squared. And so if this is equal to L plus 1, we can rewrite that the energy is equal to h bar squared over 2I L plus 1. And so our total energy is only dependent on the quantum number L and not the quantum number m sub L. Now this is very different from two-dimensional rotation, and it might be kind of hard to understand, where in two-dimensional rotation, the energy was dependent on only the quantum number m sub L. The difference comes from the fact that in two-dimensional rotation, the angular momentum L was the same as the angular momentum m sub L. It was only the z component. So here, m sub L represents the z component of angular momentum. In three-dimensional rotation, our angular momentum is now a vector in 3 dimensions. So it's not simply the z component of the angular momentum. There's also the x and y components that we have to consider. And we'll look into this next time and figure out that these operators don't commute. So we can't, like we saw with the electron, we can't know m sub L and m sub x and m sub y at the same time. So we can't actually know the angular momentum L. And we'll see what we actually can know, and it turns out there are some operators that all commute here, and these give rise to important quantum numbers. I also want to point out, again, degeneracy before we go. So some of these energy levels are degenerate. So since the energy, again, is only dependent on L, every m sub L that gives the same L will give the same energy. So if L is equal to 2, our m sub L could be -2, -1, 0, 1, or 2, and we can't distinguish between any of these. So this would be a 5-fold degenerate energy level. There are 5 different solutions, 5 unique wave functions that will all give rise to the same energy. And this is something that you could show by plugging in these various values into the Schrodinger equation. So with that, I'll let you go. In the next lecture, we're going to look at these y solutions, these functions of theta, and see what we can say about them in terms of what they look like and what kind of information we can extract out of there.